The next property to be studied in the periodic properties of the elements is the ionization enthalpy. It is also called ionization energy or ionization potential. Basically, enthalpy, energy in the chemistry is called enthalpy, and if the energy is expressed in electron volts, it's called potential. So what is ionization enthalpies? It is the amount of energy required to take out a valence electron from an isolated gaseous atom. It's called ionization energy or ionization enthalpy. So if this is what we have, our atom, and this is the valence electron, we want to remove this electron from the atom to infinity here. Definitely we have to give energy to this electron, because this electron has with the nucleus the electrostatic or Coulombic force of attraction. Now we know this electrostatic or Coulombic force of attraction is F is equal to K Q1 Q2 R square. So smaller the distance of the electron, stronger is the force, more energy is required. So that's why that's the major thing, the major formula which will give us or guide us in determining the trends of this energy in the periodic table. But first one must understand the energy required to take out valence electron from an isolated gaseous atom is called ionization enthalpy or ionization energy. Now, it means the energy which we give to make an atom converted into a cation is called ionization enthalpy. In short, it is written IE. So it is the energy which is given to the normal, neutral, isolated gaseous atom and to convert it into a cation. Now, this energy, as we have seen in the formula, depends on the first factor is atomic size. Now always remember, ionization enthalpy is inversely proportional to atomic size. Smaller is the atomic size, larger will be the amount of energy required, because more closer are the electrons with to the nucleus, stronger is the Coulombic force of attraction between them, so more energy is required to knock out electron. Similarly, when larger is the size, lesser is the ionization energy required. So what we find is this ionization enthalpy is inversely proportional to the atomic size. Second factor on which it depends is the nuclear charge or nuclear pull. The ionization enthalpy is directly proportional to the nuclear charge. The larger this nuclear pull or nuclear charge is, higher will be the ionization enthalpy. So what we find is that is why the ionization energy, as the nuclear charge increases, it also increases, because greater is that means the force of attraction from the nucleus toward that valence electron. So more energy is required than to actually take out that valence electron. So it is directly proportional to the nuclear charge. Now on the basis of these two factors, we can easily predict the trend of ionization energy in the periodic table. Now the trend is very simple. It is in a period, ionization enthalpy increases in a period from left to right. Why increases? It increases because the atomic size decreases and nuclear charge increases. So as the atomic size, we find that is decreasing, the nuclear charge is increasing. Both are the factors which make what ionization energy increasing its value from left to right in the periodic table in a period. The trend of the ionization enthalpy or ionization energy in a group is actually can very easily be predicted on those two factors which we have discussed, that in a group from top to bottom what we find is ionization energy decreases from top to bottom because the atomic size increases and the nuclear charge becomes less effective, and it becomes less effective due to the screening of the valence electron by the inner electrons. So that's why we usually find that in a group ionization enthalpy decreases. But remember, we have exceptions, or we have actually the contradiction to this statement, because it's not possible to have or to have the screening of the valence electron taking place every time. We have in the periodic table that the valence electrons are not screened by the inner electrons properly, or actually there is a poor screening of the valence electron. So whenever we find that the valence electrons are not poorly screened, we find that they are direct in contact, that they are direct under the influence of the nucleus, and as a result the nuclear pull on those valence electrons becomes higher, and it becomes difficult to take out those electrons. So that's why they shows higher ionization enthalpies. But all these are actually the studies which we will be doing in detail when we will be doing these blocks separately in your inorganic chapters. Two more factors on the basis on which the ionization enthalpy basically depends, and because of which we find that the trends in the periodic table gets little bit changed, and we get what the changed behavior of the ionization enthalpies along the period and as well as along in a group. Now the first thing which we need to know is this called penetration of suborbits. It's called penetration of suborbits, or it's also called penetration effect. We know that out of S, P, D and F suborbits, the S is most closest to the nucleus, because it is always the first one which is lying in any particular orbit. Similarly, it is followed by the P, followed by then D and then F. So these suborbits that is why having penetration effect in this type. That means S is most closest to the nucleus. That's why the electrons in the S suborbit will be more closer to the nucleus. They will be experiencing greater nuclear pull, and that's why energy required to remove those electrons will be higher. Similarly, electron, when we compare between S and P, since S has a higher penetration power, means it is more closer to the nucleus. Like if we say nucleus is here, since it is more closer to the nucleus, the electrons of the P will have a lesser ionization enthalpy in comparison to the electrons of the S. Similarly, if we keep on going away from the nucleus, like in the D and the F, we find that the ionization enthalpies keep on becoming smaller and smaller, or lesser and lesser. The reason is it's the penetration power. The best example to explain in this case what we find is that it's between your magnesium and aluminium. In case of magnesium, we have a configuration 2s2 only. So it's complete. 2s2 is almost completely filled. So then we have aluminium 2s2 2p1. So what we find in this, they all are belonging to the third, so it will be. third period, it is 3s2, it is 3s2, 3p1. So what we find is the outermost electron of aluminium is in the 3p suborbit, whereas the other two are in the s, whereas in the outermost electron in case of magnesium it is in the s suborbit. What we find is the cases that we have done that in the periodic table along the period, the ionization enthalpy increases. So as expected by the usual behavior, aluminium should have a higher ionization enthalpy. It's not correct. The ionization enthalpy, the energy required to remove the first electron, that's called first ionization enthalpy, for magnesium is found to be more than the ionization enthalpy of first ionization enthalpy of aluminium. The reason is the electrons here are in case of s suborbit, and this s suborbit is having a higher penetration effect. That's why more energy is required to remove this electron than the electron which is present in the p suborbit in case of aluminium. So, and this trend is repeated in your whole of your group 2 and your group 13, that always the first ionization energy, the energy required to remove the first electron of the second group elements will be more than the group 13 elements. The reason is, what we find is because they have the S has a greater or higher penetration power. So this is one effect. The other is the electronic configuration. Now we know that the half-filled and fully filled configurations are more stable. Now since they are more stable, stable means what? That means the more energy will be required to take out electrons from these stable half-filled or fully filled suborbits. So that's why what we find is, when we compare nitrogen and oxygen, it's 7 and 8. As studied generally, the oxygen should have a higher ionization enthalpy first than sodium, but this doesn't happen. What we find is sodium's first ionization energy is more than oxygen. The reason is because the nitrogen has the half-filled stable configuration. It's like this. It has 2p3, we are not considering the 2s, it's already filled, and this has 2p4. Now since the nitrogen p is having 3 electrons with the parallel spin, which gives it more symmetry and exchange energies, this configuration is more stable than what the oxygen is having, that it has this 4 valence electrons. Now what happens, what we notice is, therefore, though the nuclear pole is more in case of oxygen, size is smaller in case of oxygen, what we find is first ionization energy of nitrogen, and when it is compared with first ionization energy of oxygen, it was found nitrogen is having higher value. The reason, it has stable half-filled configuration. Same trend is repeated in case of phosphorus and sulfur. So what we find is that the half-filled configurations are found to be more stable. As a result, the ionization energies of the electrons in these suborbits are also higher.